Now let's talk about crystal field theory. This is what we're going to spend a significant amount of time on. Very, very simplistic way of describing bonding. Crystal field theory is used to explain the bonding and coordination compounds based upon the idea of electrostatic forces. There are two different types of forces that are important in crystal field theory. The attraction between the positive metal cation and the electrons on the ligand, and the repulsion between the lone pairs of the electrons on the ligand and the electrons on the metal cation. There are two concepts that are absolutely essential to understanding CFT. First is Coulomb's theory of electrostatic interactions. You remember this, that the potential energy between two objects are based upon the charges of the objects and the distance between them. So there's going to be more potential energy if the charges on the ions or on the charges are larger, or if the distance between them is smaller. We also have to take into account the shapes of the d orbitals on the transition metal cations. So you have to know these now, if you didn't before. So let's take a look now at CFT. What I want you to think about is a transition metal cation, any one of them, that's being approached by 6 ligands from infinity. The 6 ligands will come in and interact with the 5d orbitals. Now, so they all 5d orbitals start out with the exact same energy. They're degenerate. Now, as you bring in the ligands, the electrons from the ligands form kind of the spherical shell around the cation and increase the potential energy. Now, as the ligands get closer and closer, they're going to start coming in along the Cartesian axis, so they're going to become directional instead of spherical. So, for example, this is the dz squared orbital right here. If you have a ligand coming along the z-axis above and below the metal cation, you'll have 2 ligands interacting with the dz squared orbital. Since they're interacting with the dz squared orbital, it's going to increase it in energy. We're also going to assume that the other 4 ligands shown here by these lobes, these are the lone pairs on the ligands, are going to come in and interact with the dx squared minus y squared orbital. Remember, the dx squared minus y squared orbital lies along the x and y axes. Since the dz squared and dx squared minus y squared orbitals are oriented in the appropriate way to interact with 6 ligands, what happens is that the repulsion between the electrons on the metal cation and on the lone pairs cause an increase in energy for the dz squared and dx squared minus y squared. But at this point, let's say that it doesn't really affect the dxy, dyz, and dxz. So we have now, we're showing a different picture. We have the ligands coming in along the x and y axes. So remember, all 6 ligands are coming in along the x, y, and z axes. Notice that orbitals like the dxy aren't oriented appropriately so that the ligand orbital can overlap with one of the lobes of the d orbitals. So the dxy DXZ and DYZ are oriented so they don't interact with the ligand lone pairs. So the potential energies of these orbitals actually decrease a little bit with respect to the d orbitals in the spherical electron field. So here's what happens. Just to review, you have the free metal cation right here, right there, the free metal cation. Notice all 5 d orbitals are degenerate. They have the exact same energy. You bring the ligands in the second step, and their electrons create a spherical shell that the metal cation feels. But all of the d orbitals feel it because it's spherical. It's not directional. So it increases the energy of all 5 d orbitals. As the ligands get closer and closer, they become directional and come in along the x, y, and z axes. This causes the d orbitals to split into 2 sets. The set where the ligands interact, the dz squared and the dx squared minus y squared. They go up in energy because of the repulsions between the electrons on the ligands and the electrons on the metal cation. The dxz, dxy, and yz, since they don't interact with the ligand electrons, decrease in energy. They're stabilized by that lack of interaction. Now, I've also shown another line on this diagram, which is called the barycenter, which is the average energy of a set of orbitals in the same subshell. So notice that the barycenter has the exact same energy as the 5 d orbitals that's surrounding by a spherical shell of electrons. This splitting is characteristic of any octahedral ligand or octahedral or set of 6 ligands that come in along the x, y, and z axes, forming an octahedral complex. Now, each of these groups of d orbitals on the metal cation have names. The 2 orbitals that are destabilized by the ligand field are called EG. This is the collective name for the dz squared and dx squared minus y squared. And this comes from the idea of symmetry. I simplified it, said this is how the ligands come in along the x, y, and z axes, so the dz squared and dx squared minus y squared are the orbitals that the ligands interact with. The other set are the T2Gs. That's the collective name for the DXZ, DXY, and DYZ orbitals. Now, the difference in energy between the T2G and the EG orbitals. So these ligands coming in separate these orbitals into 2 sets. The difference in energy is called delta naught. Delta naught, that's called the crystal field splitting energy. And it represents the energies of the d orbitals due to the presence of ligands. The letter O there stands for octahedral, so this means this is the characteristic splitting for an octahedral ligand field. And it's also known, and you'll see it in some books, as 10dq.